Thank you for the introduction. Would like to say I'm very happy to be here and present this work today on behalf of my colleagues as well at the University of Surrey. So this is a brief overview of my presentation. I'll start with a quick motivation behind this work, and then I'll go through the electro-optic measurement technique that we use to measure the radiation resultant from a coaxial-to-microstrip transition. Then I'll introduce the device and the test that we used, and that will be followed with some simulated and measured S parameters. Then I'll go through the electro-optic measurement setup, followed by some measured E-field results capturing the radiation. And then I'll close this presentation with the conclusions. So as I'm sure all of you know, microwave measurements rely on vector calibration methods, which are used to obtain the S parameters of a device under test only, removing effects originating from the cables or planar structures used in the measurement, and also correct for some errors of the instrument as well. Calibration algorithms to date, such as the SOT and TRL, they rely on single mode propagation, and they also require calibration standards, which they can be found in a coaxial or a planar form. So planar structures require connectorized launchers, which are used to transition between the coaxial ports of the VNA and the planar transmission line environment. Such structures are prone to radiation losses, which can excite multiple propagation, which in turn can detrimentally impact the calibration performed and therefore the accuracy of the measurement. This effect has been thoroughly investigated by different research groups. However, the investigation was mostly relied on S parameter measurements and electromagnetic simulations. You can see one of those examples below, where on the left we have a coaxial-to-microstrip transition, and on the right the authors have simulated the E-fields in order to visualize them, where you can see they've captured a part of the radiation and some undesired coupling as well. So the aim of this work is to directly measure and visualize the electric field radiation or undesired coupling due to such transition using an electro-optic based method. Such a technique can be used to validate simulations like the one I'm showing below, and also can aid with the design of connectors, launchers, and test fixtures that planar devices are embedded within. So the electro-optic effect relies on anisotropic electro-optic materials exhibiting birefringence. So when you have, let's say, a vertically polarized input beam going through an electro-optic material, when there's an external applied electric field present, the output beam will be polarized. By detecting this change in polarization, we can directly relate it to the electric field. So the equipment that we have in our lab relies on this effect, and we're using a commercially available NeoScan electro-optic system by EMEC Technologies. This system requires the use of electro-optic probes like the one you see on the left. This probe is used to scan the area around the device under test and measure the E-field. So we have a fiber optic cable which carries the laser towards the electro-optic material, which in this case is a bismuth silicon oxide crystal. And below the crystal, there's a high reflective coating which reflects this laser back to the optical mainframe where the change in polarization is detected. The spatial resolution of this system is 8 micrometers. The E-field measurement range is between 1 volts per meter and 2 megavolts per meter, and the frequency range is between 20 megahertz and 40 gigahertz. So one of the advantages of this system is that the crystal can be cut in such a way that it experiences birefringence only by a single E-field component. Therefore, we can use a normal probe to obtain the normal E-field component, or a tangential probe to obtain the tangential E-field components separately. So this is the device under test that we used in this work, which was a microstrip transmission line designed to have a 50 ohm characteristic impedance. The length of the line was approximately 2.5 centimeters, whereas the dielectric used was a Rogers 4350 with a 20 mil thickness. In order to provide the transition, we used 2 SMA Southwest microwave end-lodge connectors, which you can see in the figure below. On the top right, you can see a close-up photograph of the transition between the microstrip light and the connector. And you might be able to also see that we slightly tapered the microstrip line in order to provide a direct connection with the pin only, avoid any shorting to the grounds of the connector. So before moving on into any measurements, first we simulated the S parameters and the E fields of this device in Keysight's EM Pro. It was easy to model the microstrip line since we were the ones who designed it. However, to model the two connectors, we've used the dimensions provided in their datasheet. And you can see the model in the EM Pro below, where we have the microstrip line and the two connectors. Whereas again, on the top right, you can see a close-up of the connector pin landing on top of the microstrip line. The frequency range of the simulation was set to 0.25 up to 10 gigahertz. So then we went and we measured the S parameters of this device, and when I say of this device, I actually mean the two connectors and the microstrip line. So we did an SOLT coaxial calibration up to the connector ends. The frequency range was again similar to the simulation was set to 0.25 to 10 gigahertz. And on the right, you can see the measured and simulated transmission coefficient and conservation factor based on the forward reflection and transmission coefficients. As you can see, the agreement between simulation and measurement is very close, and these minor differences can be depicted to the differences between the actual transition and the model transition between the connector and the line. Also, from the conservation factor, we can see that the losses increase with frequency. So in order to measure the radiated E field due to such transition, we've integrated the NeoScan system with our Keysight PNAX. Normally, the NeoScan system is used in a lock-in configuration, which enables signal frequency measurements. However, by integrating this system with the Keysight, we can perform multiple frequencies by sweeping the operational frequency of the PNA. All this equipment that I used in the schematic was control using a custom LabVIEW software. So port 1 of the PNAX was used to provide the excitation signal to the microstrip line. The other end of the microstrip line was terminated to 50 ohms in order to, we wanted to have a transmission line structure which could have been used, for example, in a TRL calibration. The NeoScan system outputs a time domain signal which we receive on port 2 of the PNA. Therefore, by measuring S21 in this case, the output signal of the NeoScan system is referenced to the excitation signal provided to the microstrip line. Also, the E-field measurement results that we show in this work are normalized to their own maximum. Absolute E-field calibration is possible, however, you would require a micro TEM cell, and also it is not required to assess the behavior of the fields. What you can also see in the figure is you can see a motion controller and a translation stage, which are used to manipulate the probe around the device under test area. So the schematic I've just described is also shown here in a photograph. On the left, we have the PNAX. We're using port 1 to provide the excitation signal. On the right, you can see the translation stage and the probe holder. The electro-optic probe itself and the device under test, which in this case is a bit hidden, but I'll show a close-up photograph of this configuration in a second. And at the back, we have the NeoScan system, which outputs the time domain signal received by the PNA. Any of the other ports of the PNA can be used, as long as you measure the corresponding transmission coefficient. So before measuring the E field leaving essentially the microstrip line, essentially capturing the radiation, we measured we scanned an area around the microstrip line. So the microstrip was measured at 2.2 gigahertz, and the results we're showing here were published last year. The magnitude and phase of the E field was obtained above each point in the scanned area. And we can also plot the time domain E field response using the equation on the left. On the right, you can see on the two top plots the normal E field measurement components, so EZ in this case, and one of the tangential ones with EY. Below, you can see the simulation of these E field components, which they show a very close agreement between measurement and simulation, providing confidence that our model is quite accurate. In order to measure the E field leaving the microstrip line, we had to rotate it by 90 degrees. And the reason we did that was the translation stage enables the horizontal two-dimensional movement of the probe. Therefore, by rotating the microstrip line by 90 degrees and placing the electro-optic probe in front of it, we could scan above the conductor line the field leaving the device under test. On the left, you can see on the photograph the excitation signal, the microstrip line, and on front of the microstrip line, the electro-optic probe, which in this case, a tangential electro-optic probe was used, even though we're measuring the normal to the microstrip E-field component. On the right-hand side, we have the 50 ohm termination providing us with a transmission line structure. So this is the actual scanned area that we performed the measurements to. The step size for the measurement was set to 250 micrometers in both the X and Z directions. And the probe's initial height was set to 100 micrometers above the transmission line conductor. The excitation signal power of the PNA was set to 10 dBm with an IF bandwidth of 10 Hz and an averaging of 15 tweaking is the signal to noise ratio. And the frequency range was set from 1 to 10 gigahertz. Now you can see actually the microstrip line placed in a normal configuration. And the area between the two connectors scanned was 5 millimeters by 13.5 millimeters, whereas above the line again and now part of the two connectors, the area was 10 millimeters by 33.5 millimeters. So in this presentation, I'll show measured and simulated results at 3 different frequencies, and I really want to emphasize that the figures below that you'll see in the next 3 slides are actually measured results. On the left-hand side, I've kept the figure from the previous slide as a reminder of the scanned area. And what we're going to see, we've animated both the simulated E-field and measured E-field. So what you'll see in these animations, which I hope they run smoothly, is the E-field travels from left to right, and most of the E-field is confined around the microstrip area, providing with an essentially expected response. As you can see, we can still measure some E-field at the two transitions, so you can imagine that that's the area over there. However, again, most of the E-field is confined around the microstrip area. Now, at 7 GHz, something very interesting is happening. So, instead of the E-field being launched into the microstrip line, a portion of it will actually couple back from the connector on the right back to the connector on the left, and the E-field now above the two connectors is even stronger. Again, you can see the coupling in both the measurement and the simulation. And sorry if there's any delay between them. I guess this has to do a bit with the processing power of the PC. However, again, you can see that the E-field, rather than being launched into the connector and inside the 50 ohm load, actually some of it radiates. Now, at 10 gigahertz, the effects I've just talked about happening at 7 gigahertz, they're even more enhanced. And also you can see a portion of the E-field detaching from the microstrip line structure and radiating into air. Again, now you can see that the wavelength is where at 10 GHz is smaller. The coupling is still happening. Some of the E-field is radiating. And you can see instead of being launched into the microstrip line, it actually leaves above the connector. So to conclude, the system I've just described enables a direct measurement and imaging of the electric field radiation due to coaxial-to-microstrip transition. Such a system can be used to validate simulations like the ones we've just shown, and also can help with the design of connectors, launchers, and test fixtures. The measured E-fields showed a very good agreement with the simulation at frequencies up to 10 gigahertz. And as next steps, we would like to investigate this effect at even higher frequencies and also investigate different transitions such as ground signal ground probes used with on-wafer standards and structures. As a group, we would like to thank EPSRC, Ampere, and more specifically the Advent project, and RFTAC for the generous financial support. Thank you for your attention, and I'm happy to answer any questions you may have.